This is a revision video for AQA GCSE Combined Science or Chemistry Unit 1, which is atomic structure and the periodic table. For your GCSE Science, 40% of the marks are for pure factual recall. So this is a series of questions so that you can test yourself on whether you can actually recall those facts from the spec. Once you're confident that you've memorised everything in the specification, then you can move on to trying to apply that knowledge and looking at data analysis questions and evaluation questions. For GCSE Science, we just need to know that there are about 100 elements. Even though scientists have currently discovered 118 of them, for GCSE we just want to know about 100. Those elements are listed in the periodic table. Compounds are substances formed from elements by chemical reactions. They contain two or more elements chemically combined in fixed proportions. Chemically combined is just a different way of saying bonded, and in fixed proportions just means that we can use a symbol formula to show that, say, there are always two hydrogen atoms bonded to one oxygen atom in water. Compounds can be separated back into their elements by chemical reactions. To name compounds, we have two rules. If there are only two elements, then the metal, which is the first element, just stays as it is, and then for the second element we take the first syllable and we put "ide" on the end. So for instance here we have sodium chloride and magnesium oxide. If there are three elements and the third one is oxygen, then we start the same. The first element stays as it is, the second element we take the first syllable, but then we put 8 to show that there's also oxygen there. So this last compound is copper sulfate. A mixture consists of two or more elements or compounds that are not chemically combined together, they're just mixed up, and they can be separated out by physical processes. The chemical properties of each bit of that mixture haven't changed at all. Filtration is used to separate out insoluble solids from liquids. So for instance, if you had some sand mixed into some water, you could separate it out using filtration, using some filter paper and a funnel. You can't separate a soluble salt by filtration because the soluble salt will just go straight through the filter paper because it's been dissolved. So what you do instead is crystallization. That's where you put your solution into an evaporating basin and you maybe gently heat it over a Bunsen burner or a water bath until all of the liquid has evaporated and you're just left with the soluble salt. Distillation isn't a chemical process because it doesn't involve a chemical reaction. It just involves heating something up until a liquid evaporates at its boiling point. The chemical properties of that liquid haven't changed, so it's not a chemical process. Fractional distillation and chromatography can both be used to separate mixtures of liquids. If you're wanting to go on and use those different liquids for different things, then you'd use fractional distillation. So for instance, we use fractional distillation when we have crude oil and we want to separate it out into natural gas and petrol and diesel and naphtha and kerosene and all those different fractions which have different uses. Chromatography is usually used on much smaller samples, and we use it when we're trying to analyse the mixture rather than particularly go on and use things. So you'll have done paper chromatography in your classroom because it's one of the required practicals that comes up much later in the specification, and there you'll have been separating out different kinds of inks. But at the end, you don't have the inks, you can't use them for anything because they're stuck in the piece of paper. So it's more of an analytical method rather than a separation technique. You need to know about the history of how the model of the atom has changed over time, and it's used as an example to basically show how as time's gone on and we've found more evidence, we've changed the model to take account of that evidence. So John Dalton was a British chemist, he was one of the first to talk about atoms, and he visualised them as just being like hard spheres. He compared them to billiard balls, which are basically snooker balls. So he said that they were hard, indivisible spheres, they couldn't be broken up into different parts. J.J. Thomson then came up with the plum pudding model because the electron had been discovered. So he knew that there were these small negative particles which were part of the atom, but he didn't yet know where they were. So he visualised this as being like a ball of positive charge with the negative electrons embedded in it, and he compared it to being like a plum pudding, which you've probably never seen but is basically a Christmas pudding, where the sultanas represent the electrons. Ernest Rutherford and his students were responsible for the discovery of the nucleus when they fired alpha particles at a sheet of gold foil in what's called the alpha scattering experiment. So you'll have learnt in physics that an alpha particle is 2 protons and 2 neutrons stuck together. It's basically a helium nucleus. And based on how those particles behaved, he was able to show that actually the vast majority of the atom was just empty space, and at the centre of it was this teeny tiny nucleus, and that was where most of the matter was condensed. Later, Niels Bohr changed the nuclear model because he said that rather than there just being electrons round the outside in a single ring, which is kind of what we'd assumed, they were actually at fixed distances from the nucleus, what we now call shells. In 1932, James Chadwick did experiments which demonstrated that there were neutrons in the nucleus as well. And this was really important because it allowed us to start talking about isotopes. An atom is the smallest part of an element that can exist. It has a radius of about 0.1 nanometers, which you need to know is the same thing as 1 × 10 to the minus 10 meters. Even though we usually draw it really large, the nucleus of an atom is actually only 1/10,000th of the whole of that atom. Almost all of the atom is actually empty space. The atomic number of an element tells you how many protons it has, and you'll find that for AQA on your GCSE periodic table, it actually says atomic brackets proton brackets number. The relative atomic mass of an element tells you how heavy it is compared to carbon-12, which is the standard atom. It's made up of the mass of the protons and the mass of the neutrons. So if you know the relative atomic mass and you know the number of protons, you can use that and do a little subtraction to work out the number of neutrons. The three subatomic particles, or particles smaller than an atom, are protons, electrons, and neutrons. Protons have a relative charge of +1, electrons have a relative charge of -1, and neutrons have a relative charge of 0. Anytime that you see the words relative charge used, it's really important that you're using numbers rather than just saying positive, negative, neutral. Because what relative means is we're comparing the sizes of those. So if we say +1 and -1, we know that the size of those charges is the same. Whereas if I just said positive and negative, well, a proton could have a positive charge that's 5 times bigger than an electron. And that's important because if that was the case, then they wouldn't be able to balance each other out, and we know that they do. Protons and neutrons have a relative mass of 1, which means that they weigh the same amount as each other, and the relative mass of an electron is very small. You don't need to know an exact numerical value for it, but you do need to know that it is not 0. Electrons do have mass. The nucleus contains the protons and the neutrons. The electrons are not there in the nucleus, they're around the outside in the shells. Atoms have no overall charge because they have the same number of protons and electrons. And we know that protons and electrons have charges which are the same size, the same magnitude, but opposite polarity. To calculate the number of neutrons in an atom, you take the relative atomic mass and you subtract the atomic number. Isotopes are different atoms of the same element which have the same number of protons, because the proton number is what defines something as a certain element, but they have different numbers of neutrons. Because they have the same number of protons, they also have the same number of electrons, because we know that those are equal in an atom. That means that chemically these isotopes behave exactly the same, because in chemical reactions it's the electrons that get involved. Physically, they're quite different. For one thing, isotopes are going to have different masses, because they've literally got different numbers of particles in their nucleus. That's also going to affect their density, their melting and boiling point, and even their radioactivity. Electrons are found in the shells, orbiting the nucleus. When you're drawing an atom, you always start by putting the electrons in the innermost shell, and you're not allowed to move on until that innermost shell is full. The first shell can fit 2 electrons in, the second shell can fit 8, and the third shell you're going to draw 8 electrons before you move on to the fourth shell. The modern periodic table arranges elements in order of their atomic number. The columns of the periodic table are called groups, and the rows are called periods. The metals are towards the left. Elements that are in the same group have the same number of electrons in their outer shell, and that's going to be the same as their group number. So say everything in group 1 has 1 electron in its outer shell, everything in group 2 has 2 electrons in its outer shell. And because it's electrons that take part in chemical reactions, that means that the elements in the same group have the same chemical properties. So say everything that's in group 1 is really highly reactive, and everything that's in group 0 is completely noble, completely stable and unreactive. The periodic table is called the periodic table because periodically means happening at regular intervals. So every time we come back to group 1, we find another very soft, very reactive metal. The early periodic tables put elements in order of atomic weights. The reason for that is that when the first periodic tables were being constructed, nobody had even discovered a proton yet, so we couldn't arrange things by proton number or number of electrons or anything else because we didn't know those particles existed. When scientists were first trying to write a periodic table, they hadn't discovered all the elements yet. They only had about half of them, and so for that reason they were incomplete. Dmitry Mendeleev was the Russian chemist who was innovative because he left gaps in his periodic table. He wanted to keep elements that had similar chemical properties together, so when he didn't have an element that fit the pattern, he left a space and then he made a prediction about what he thought would go there later. He also occasionally swapped elements round when he thought there was something funny about them and they weren't quite in the right place. Later, as we discovered more elements, we found that pretty much all of Mendeleev's predictions were correct, and so that gave a lot of evidence to suggest that his table was the right table, and that's why it's been so readily adopted. Group 1 are the alkali metals, and they're not called this because they're alkalis. You know that an alkali is something with hydroxide ions, and they're just metals. So they're called the alkali metals because when they react with water, they make metal hydroxides. Lithium reacts with water to produce lithium hydroxide and hydrogen. You can test for any hydroxide by using an indicator or a pH probe. So for instance, universal indicator will go blue in the presence of any alkali, and every hydroxide is an alkali. To test for hydrogen, you need to do your squeaky pop test. You ignite it, which means setting fire to it, and if it's hydrogen, it will burn with a squeaky pop. The atoms of lithium, sodium and potassium all have one electron in their outer shell. As you go down group 1, the elements become more reactive. This happens because the atoms are getting larger and they're also having more shells. When elements in group 1 react, they do this by losing one outer shell electron. So the larger the atom is, the further that electron is away from the nucleus, and the less pull it feels, the less electrostatic attraction there is, trying to keep it held onto that atom. The remaining electrons, which are in the inner shells, are also shielding the electron, so they're kind of stopping it from feeling the pull of the nucleus. So the more inner shells there are, the easier it is for that outer shell electron to escape. Potassium is further down group 1 than lithium. That means it's going to be more reactive. So it's going to move faster on the surface of the water, it's going to produce more bubbles, and it may also ignite and burn with a lilac flame. The group 1 metals are kept under oil because they're so reactive, and the oil prevents them from reacting with oxygen in the atmosphere and also water. The group 1 metals react with chlorine to produce metal chlorides, and these are white soluble salts. So you're very familiar with sodium chloride because that's just table salt. Compared to the transition metals, the group 1 metals have very low density, so if you put them in water just at the same time as they start reacting, they float on the surface of the water because they're less dense than water. They're also very soft, you can literally cut them with a scalpel. The reason that they're soft is that the bonding in metals is created by the electrostatic attraction between the outer shell electrons, which have been delocalised, so they're sort of free to move around, and the remaining positive ion. Because the group 1 metals only have one electron in their outer shell to begin with, when they lose that one electron, when it becomes delocalised, they're forming ions that have a single positive charge, and each atom is only contributing one delocalised electron. If you compare that to the transition metals, where there are usually 2 or 3 electrons being delocalised, the strength of the electrostatic force of attraction for the group 1 metals is less because you've got a lower charged ion and also you've got fewer electrons to be attracted to it. Group 7 are called the halogens. Fluorine, chlorine, bromine and for that matter all of group 7 have 7 electrons in their outer shell. As you go down group 7, they become less reactive. So this is the exact opposite of group 1. This is because when group 7 react, they're not trying to lose an electron, they're trying to gain one. That electron is gained when it's pulled towards the nucleus of the group 7 atom. So the larger the atom is, the further away the nucleus is having to exert a force. Group 7 elements are found in small molecules consisting of pairs of atoms covalently bonded together. As you go down group 7, the boiling point rises, so whereas fluorine and chlorine are gases, bromine is a liquid, and by the time you get to iodine, it's actually a solid. This is because between the molecules, there are weak intermolecular forces of attraction. And as we know, as molecules get larger, so do their weak intermolecular forces of attraction. So the forces between molecules of iodine are stronger than the forces between molecules of fluorine. Therefore, it takes more energy to overcome those forces, and whereas there is enough energy at room temperature to overcome the forces in fluorine, there isn't enough energy to overcome those slightly larger forces between iodine molecules. Group 0 are known as the noble gases, because noble means unreactive. Helium, neon and argon all have a full outer shell, so helium has 2 electrons in its outer shell, and then all the others have 8. This makes these atoms incredibly stable. They basically never form compounds unless they're forced to, and even then it's only the larger elements that are able to do this. As you go down group 0, the boiling points increase, and this is for the same reason as with group 7. As you go down the group, the atoms are getting larger, and therefore the forces between them are also getting stronger, so it takes more energy to overcome them. Even at the bottom of the group though, they're still pretty weak, and that's why everything in group 0 is a gas. This last bit is just for the triple scientists, so if you're taking GCSE Combined Science, you can switch off now. The transition metals are found in that central block between group 2 and group 3 of the periodic table. They're hard, they have high melting and boiling points, so they're solids at room temperature. They're good conductors of heat and electricity, and also they're malleable, which means that they can be bent or hammered into shape. Transition metals make really good catalysts. They form ions with different charges, so for instance, copper can make a 2+ ion, but it can also make an ion with a single positive charge. The transition metals also form compounds with specific colours, so for instance, anything with iron 3+ ions in it has a sort of orangey brown colour like rust, whereas iron 2+ ions give a dark green colour. Lots of transition metals are used to make jewellery, like silver, gold, platinum, copper, and the reason for that is because they're much less reactive than, say, your group 1 alkali metals. So they don't react with the oxygen in the atmosphere very quickly, and that means they stay shiny for longer.